The separator. Test separators are versatile pieces of equipment that allow separation, metering and sampling of all phases of the effluent.
Because test separators are used on exploration wells where the effluent is unknown, they must be able to treat widely varying effluents such as gas, gas condensate, light oil, heavy oil and foaming oil, as well as oil containing water and impurities such as mud or solid particles.
The separator is the principal part of the process system.
It manipulates the stream of produced fluid to take advantage of the density differences that exist between gas, oil, and water, and that causes these phases to separate.
Because of the relative densities of gas and liquid, their separation is quick, usually a few seconds.
Some liquid may remain for a time in the gas in a fine mist. Densities of oil and water, however, are closer and can take a few minutes to separate.
Inside the separator there are several pieces of equipment to help the process. The test separator is mainly composed of effluent inlet, deflector plate. A flow breaker or deflector plate is placed in front of the inlet.
The gas flows round the breaker and the liquid falls to the bottom of the vessel.
Coalescing plate. Dixon or coalescing plates arranged in an inverted V-shape group small droplets of oil into bigger drops which under the action of gravity, trickle down into the liquid. Gas leaving the coalescing plates may not yet be dry. Foam breaker.
A wire mesh foam breaker prevents waves of foam passing along the separator and being carried away with the gas.
Mist extractor.
Before leaving the separator, the gas will pass through a mist extractor composed of a mass of wire mesh. It is designed to stop tiny oil droplets down to 10 microns from leaving the separator out of the gas line.
Weir. If the level of the water is controlled, a weir placed in the bottom of the vessel will allow only oil to overflow and spill into the oil compartment. Vortex breaker.
Oil and water pass through vortex breakers on the outlets to prevent gas flowing out these lines.
Oil level controller.
When the oil level changes, according to the principle of Archimedes, the plunger will be buoyed up by a force equal to the weight of the displaced fluid.
Water level controller.
The controller can be adjusted for throttling action if there is a steady flow of water, or for snap action if the water is to be drained at one time.
Oil, water, and gas outlets. Pressure safety valves. Manhole to service the separator during its maintenance. The separator's vessel capacity for each phase depends on the current conditions of pressure and temperature and effluent properties such as viscosities and densities of the liquids, which are a function of the amount of dissolved gas vessel operating. Liquid level. Vessel internals. Required liquid-gas separator efficiency in terms of size of liquid droplet to be separated from the gas phase. The separator's control system includes gas line control, wizard, 1 3-inch PCV, pressure control valve, fail-safe open to release vessel pressure if air supply is lost, oil line control, leveltrol, 1 1-inch and 1 2-inch LCV, liquid control valve.
Fail-safe close to retain oil, minimize pollution if air supply is lost.
Water line control, leveltrol. 1 2-inch LCV, liquid control valve.
Fail-safe close to retain liquid, minimize pollution if air supply is lost.
Pressure control.
When gas line pressure drops, Borden tube contracts, closing nozzle, relay switches allowing pressure build up to close valve. As gas line pressure rises, Borden tube expands, opening relay and releasing pressure from valve allowing it to open. Pressure control proportional band. The proportional band valve reduces the response time of the valve to act as a damper and prevent oscillation of the valve, and therefore, reducing pressure oscillation in the separator vessel. The full range is 1,500 psi. 10% on the proportional band, it means 75 psi before valve open or close fully above and below set point.
Level control. With low level, flapper nozzle is open to atmosphere. Pressure cannot build up and valve remains closed. As level increases, float rises, closing the nozzle with the float. Pressure builds up and valve opens. Level control proportional band. The proportional band valve reduces the response time of the valve to act as a damper and prevent oscillation of the valve. The full range is 12 inches. 10% on the proportional band, it means 0.6 inches before valve open or close fully above and below set point. The separator is used to meter the different phases of the effluent, oil, water, and gas. The gas metering consists of a Daniel orifice and a Barton chart recorder. The oil metering consists of a 3-inch Rotron vortex meter for high flow rates and a 2-floco positive displacement meter for low flow rates. The water metering consists of a 2-inch floco positive displacement meter. The positive displacement meter measures the liquid passing through it by separating the liquid into segments and counting the segments. Liquid entering the meter strikes the bridge and is deflected downward, hitting the blades and turning the rotor in the right direction. The seals on the bridge prevent the liquid from returning to the inlet side. The rotor movement is transferred to a register readout device with magnetic coupling. The ball vortex meter consists of a body with an offset chamber and a rotor that are mounted transversely to the flow stream. When liquid flows through the meter, a vortex is created in the offset chamber. The rotational velocity of the liquid vortex is proportional to the rate of flow. The rotor movement is transferred to a register readout device with magnetic coupling. The Daniel orifice meter. Orifice plate generates a differential pressure which, when combined with static pressure and gas temperature, allows a gas rate to be calculated. At the beginning of a test, the gas flow rate is unknown. During the test, the gas flow rate may change, therefore, different sizes of orifice plates are used. It's important to have an apparatus that allows the orifice plate to be changed without interrupting the gas flow. The orifice gas meter is designed for this purpose. To obtain accurate measurements, the flow of gas must be streamlined before it reaches the meter. An adequate length of straight pipe and straightening vanes, bundle of straight tubes fitted inside the pipe, are positioned before the meter to reduce the disturbances created by the elbows in the gas line. To record the differential pressure, a measuring instrument called a differential pressure recorder is used. The high-pressure side of the recorder is connected on the upstream side of the orifice and the low-pressure side is connected on the downstream side. The movement of the recorder is transferred to a pen that records the differential pressure on a chart. The same chart is used to record the static pressure, measured downstream of the orifice plate. In addition, another pen is used to record the gas temperature. The Barton chart recorder records the gas differential pressure using the blue pen and records the static pressure downstream of the orifice with the red pen. It may also record the gas line temperature using a green pen. Note that the colors given here are for the normal situation. Make sure you check your rig up for any possible changes. The gas used to operate the differential pressure recorder is provided by the separator gas line. This gas is first filtered on both the high and low pressure lines using bottom gas scrubbers. These gas scrubbers are vertical pots where impurities, oil, and emulsion settle. Before the gas reaches the recorder, it is filtered again by the top gas scrubber. The top scrubbers act as a buffer between the gas and the recorder. In case the gas contains H2S or CO2, sour gas, the top scrubbers can be filled with hydraulic oil or diesel to prevent direct contact between the gas and the recorder. The shrinkage tester, usually attached to the oil sight glass of the separator, is used to estimate the shrinkage factor in the field. The shrinkage factor is a correction factor used in the oil volume computations. It represents the amount of dissolved gas in the oil that will be freed when the pressure drops from the separator pressure to the atmospheric pressure. Relief valves are installed on all pressurized vessels to protect the vessel from being pressurized above its working pressure. On the separator there is two valves, normally a pilot-operated relief valve set to open when pressure exceeds working pressure. The picture shows an old-type relief valve. This isn't the pilot-operated valve. The basic principle can be understood by looking at this type. If the separator pressure acting on the piston exceeds the spring force acting opposite way, the valve lifts from the seats and open. On old separators, a rupture disc is installed instead of one of the relief valves. The rupture disc has a set pressure to open when pressure exceeds 110% of the separator's working pressure. The problem with the rupture disc is that it will not close when pressure in the vessel goes below working pressure. The sight glass is a weak point on the integrity of the separator. Because of this, two safety valves are installed on the ports to the separator. Both will shut if the flow past them exceeds their design point. Please hit like and subscribe to our YouTube channel to help us produce more content like this one. Thank you for your attention.